Yeah, so I'm going to talk about cyber physical systems, but what I'm going to talk about applies to hardware software systems based on designing a controller to control a system. So first I'll start off talking about what we mean by a cyber physical system, and then I'll talk about the Rodin technical approach and the method. And Rodin is the tool set that we use. And then what I'd like to do is actually go through a simple example just to show how the method works, talk about the application domains, and then summarize. Okay, so this is a reasonable definition of what a cyber physical system. So it's an integration of computing and physical mechanisms. So this is a difference. There's something physical, mechanical, hydraulic, and it provides these physical services, which is transportation. So this is rail or automotive, energy distribution, that's smart grids, medical care, manufacturing. And as they become more complex, you want them to be adaptable, efficient, and particularly safe and secure. Probably they should be secure there as well. So I guess the first question is, what's the difference between a cyber physical system and an embedded system? It's a controller running some sort of system, and the answer, there isn't really a difference. It's really based on how you model the environment. So in these typical applications, when you actually do your verification, the environment is going to not be discrete. It's going to be continuous. So here we are in the world of MATLAB. So the history of these systems has come from development and verification, which has been done mainly with MATLAB. Whereas I think if you look at what happens in EDA, you need to deal with timing, synchronous, stuff like that. So if you look at this history, you'll see that the problem that they've had just using MATLAB is that they don't have really clean temporal semantics. Now, this is probably a problem that we know how to deal with synchronous design. This very interesting paper by Edward Lee from Berkeley. And they've struggled. So effectively what's required is a hybrid approach. You need to have the strengths of EDA tools, which deal with timing very nicely, but you also need to be able to model a continuous environment, and that's what I'm going to talk about. Okay, so I'll give you, first of all, an overview of our approach, and at all stages, we focus on the key role played by modeling. So you've all heard about model-based development, model-based design, model-based verification. Modeling is used at every stage of the development process, right from the beginning, right through from requirements analysis. So we apply the modeling at the requirements level all the way down to acceptance testing. And we augment this formal refinement-based modeling with simulation and testing. So this is a difference. In this Rodin environment, you can do formal theorem-based proving, but you can also do model checking and simulation and testing, all in a single environment. Okay, so first of all, let's talk about the areas where Rodin is used. Now, as she said, we're verification guys. That's our background. But verification is just part of the problem. So this is a part of the problem, requirements capture, specification. Rodin has a language called Event B, formal modeling language. It's a mathematical language based on set theory and first-order logic. It has a textual input. It also has a graphical input. So if designers like writing UML, we have a formal way of bringing in UML state machines into the system so that designers don't necessarily need to operate at the textual level. I'll show you some text later on, and I don't think it's that difficult, and you probably don't need a PhD to write it. So once you have a formal model, then you can start talking about proof. So built into Rodin is a notion of proof obligation generation, which is done automatically. So you write your model, you write it in an event-based way, which is much more similar to Verilog or VHDL. Proof obligations are generated, and then we can talk about invariant preservation and refinement checking. You start off with an abstract model from the specification. You refine towards an implementation, starting off untimed, then moving down towards a timed implementation. What formal refinement checking gives you is that the refinements of the model have to preserve the properties of the abstract model. We can also do model checking. So the nice thing is, as you write your model, you have a choice. You can run proof, and you can run model checking. So here we have invariant preservation. We can prove it. If we can't prove it, we can run the model checker, and we may then be able to get a traceback of why we can't prove it. So using these two in combination is very nice. We can also check violation deadlocks, and the other thing we can do is check deadlocks. So in proof, typically is not so amenable to dealing with deadlocks, but model checking can be. What I will talk about is you can actually do deadlocks at the proof level as well. Okay, so that's capture and verification. So model validation. So what's very, very important, and that's been talked to by a number of the speakers earlier, is you need to be able to trace your requirements. So built into Rodin, we have a plugin that uses this open Recif exchange format, and that enables you to trace right up from the top level specification right down towards the implementation 2 ways. And that's going to be important for coverage as well, which I'm going to talk about. Again, this was talked about this morning. From a validation point of view, you're working with domain experts. They're probably not simulation experts or formal experts. You need to be able to have a dialogue with the domain expert to actually show that the model that you're writing from his specification actually does what he thinks it does. So we're able to animate, and we're also able to have graphical animations of the model. So you can draw a particular diagram, and you can execute the model on the simulation engine and actually animate the diagram. So if you think about it, if you're in a power distribution application, you would show how voltage is changing across a network. As we come back to verification, now we need the notion of coverage sign-off. Is our formal tools able to provide some notions of coverage? And I think the answer is yes, more and more. So as you come down to the implementation, you can start doing model-based testing. You have a model. It's a formal model. You've done some proofs on it. You can use the model checker to actually generate tests for you. But even better than that, you can actually measure MC/DC coverage on the model right from the beginning. So we actually start at a very high level to model MC/DC coverage because in general, we're modeling state machines of the controller. And even at a high level, you can start writing state machines without reachable states.
Sorry, John, can you just elaborate what is MC/DC?
Modified condition decision coverage. This is the sign-off criteria for aerospace software and hardware. And I'm sure all the simulators that I know of have a coverage capability that will allow you to measure MC/DC coverage. So you start off at a very high level with a single abstract event. This may be establish a communication link. So you just have an event in your state machine. I've initialized. I want to establish a link, and I move on. It's an atomic transaction. So you think about it at TLM level. It can be defined as an atomic action. Then as you refine that, you take that, establish a communication link. You want to initiate the link. You want to retry. You want an error. You want to succeed. And so as you refine this event into multiple events, you want to be able to measure the coverage. And you want to know that when you start testing it, because even at this very high level, you're already thinking about how you're going to test it. Have I covered all the possibilities of the way this model can be exercised? MC/DC coverage can be measured on the model using the model checker or directed tests or a combination of both. So very early on in your process, you're already having some idea of how you're going to cover this system. And then as you come further down, then you want to co-simulate because you can have an implementation. You may be reusing blocks of RTL. And what you want to be able to do is now co-verify the implementation with the model. You can run that as a co-verification with the test bench that's been generated here. Look for errors here, and then look for errors in the actual implementation. And what it also enables you to do is it links the structural coverage that you're measuring on your RTL implementation with the model coverage that you've already been measuring at the higher level. So the co-simulation framework, and this is really why I've been talking about cyber-physical systems, is that there's no way that a single tool vendor is going to be able to provide a simulation environment that will work with all the different environments that are needed for these cyber-physical systems. So what this co-simulation environment allows you to do is to model the environment in MATLAB or Modelica and then link it with your discrete model. And then you can also take, if you have a hardware block which is discrete logic, you can simulate that as well. So you can have multiple simulators cooperating. And the interface we use is a very strange name. It's called the Functional Mockup Interface, FMI. And this is a European automotive standard for modeling. So if you look on Mercedes' website, you'll find that already automatic gearboxes that have been developed by Mercedes are verified using this functional mockup interface. And this is what the simulation looks like. So you have, in this case, this is a local smart grid of a set of houses which may have, it has some sort of voltage generator, and it has a transformer here. And the transformer taps can be altered to make sure that the load matches within the range of 220 or 230 volts. And then you want to develop a controller. So this is an event B controller, which is going to control that tap changer. And this is a state machine. So the engineer describes the state machine with some notion of timing, which is going to control this. And we model this continuously. And then what we're able to do is simulate this. So this is at the back-end verification. We can model as the voltage drops from 230 down to 228, which is the limit. Then the controller can institute a tap change. The voltage can go up again. So that gives you a flavor of how that works. Right, what I'd like to do is go from top almost to bottom with a simple aerospace example. So I'm just going to take from a landing gear system, I just want to talk about the landing gear doors. So do you have a specification? You know, where's it written down? What you need to establish, and this is a human operation, you've probably got pages and pages of Airbus specification. What you want to do is establish with the domain experts, what are the critical things that we need to control? What is the controller going to control? The controller is going to open the doors. It's going to open the doors of the landing gear when the pilot moves the lever to extend or retract the landing gear. So the pilot is controlling this, pulls the lever to extend. First, the doors are going to open. The controller then closes the door when the gear is fully extended or retracted. And here, we can almost see now formal properties arising. The doors will remain open while the landing gear is extending or retracting. So already at a very high level, you're starting to think about the properties that you want to describe about the system. You want to be able to prove those at the high level, but then retain these properties right through the system. So effectively what we're talking about is safety requirements, but this doesn't apply just in safety critical areas. Any high consequence system, any controller, human or automated, needs a model of the process being controlled to control it effectively. I think it's a very nice, simple statement. So we're going to design a controller, but we're going to actually put a model of the system into that controller. So we'll be able to detect faults. We'll be able to detect when bad things happen. Accidents can occur when the controller's process model does not match the state of the system being controlled, and the controller issues unsafe commands. This is a very interesting book that's available online. So this is the fundamental philosophy about how we determine these high-level properties of the system. And we use a system called System Theoretic Process Analysis, which is also described in the book, STPA. Identify potentially hazardous control actions, and then derive the safety constraints from that. And then determine how these unsafe control actions can occur. And so from a controller point of view, this is a very typical diagram of how you do this high-level system analysis. So the controller has a model, as I've said, of the door. The door position is either locked open or locked closed. It's opening or closing, or it may be unknown. So this is when you have faults. You have to deal with a case when the actual hardware-software controller actually doesn't know what's happening. You have a human operator. The human operator also has a model of what's going on. The landing gear is extending or retracting or unknown. The human operator can move the lever, which can cause the extend or retract of the door subsystem to occur. And you have the typical controller loop, where you have a sensor, which can tell the controller whether the door is locked open or locked closed, and an actuator, which will cause the door to open or close. So this is the fundamental analysis. And then very briefly, you can do this in a very systematic way. And this is a very good way of dealing with the fundamental control variables of your system. Is we have two controller actions: open the door, close the door. What happens if I don't open the door when I should open the door? This would cause a problem with the landing gear. What happens if I open when I shouldn't? It's not hazardous. So you just go through these scenarios systematically, and from that we can derive some constraints, properties of the system that we want to preserve. If the landing gear is extending, the doors must be locked open. So already we have properties that we want to prove. If the landing gear is retracting, the door must be locked open. And a closed door command must only be issued if the landing gear is locked up or locked down. An open door must also, only when it's locked up or locked down. So this analysis, we use this in safety critical, but even if it's not safety critical, we always use the same type of analysis. We check this out with the domain experts, and now we have the step. We want to take that natural language requirements and specify them in event B as safety constraints, which are derived from there. And then we want to link back from our formal constraints back to the natural language. So now I'm going to show you a little bit of mathematical event B. So from that natural language, we can say something very formally about the system, a property, even at this very high level, that must be preserved right down to the implementation. And this property is an invariant of the system which says that the gears, either the gears are locked down or locked up, or the doors are locked open. So the gear state's locked down or locked up. If it's not in the state, the gears are actually moving, then the door has to be open. That's very simple. So that's the invariant of the system, and it's a natural step from the natural language to that invariant. Now we have a bit of event B. And event B is a very simple form of language because this is all you write. You write events. So we have an event which is close. So when the pilot pushes a lever, an event can be enabled depending on its guards. And if the guards are enabled, then the action happens. So it's really, really simple language. So if the gear state is locked down and locked up, and the door is opening or locked open, then only then we can close the door. This isn't very, very difficult for developers to understand, because it's in a question of people understand this close is part of a state machine. It's a transition on the state machine, and these are the guards that guard that state machine transition, and that's the action on the state machine transition. So from this, we can develop the state machine, and we can have a high-level model in terms of just two variables, the gear and the door. And so initially you start the gears, well, you start down here, gears locked down. You're on the ground, gears locked down, doors locked open. There's a command that's issued, abstract level is open, you move to the state of opening. If nothing else happens, you can complete the open, then you can retract, and eventually you'll get to a point where you have the gear locked up and the door closed. Now already you have a notional abstract state machine for the system, and when you test, you want to cover these arcs. This is an untimed abstraction, but now we want to be timed, because there's going to be delays, there's going to be deadlines on these actions of the system. And so what we need to do is take this untimed model and refine it to introduce sequences of temporal events. So what we do in event B is we actually implement synchronous timing semantics, which are the same as HDL, Verilog or VHDL cycle-based semantics. And it also enables us now to start thinking about our invariants as assertions, either system Verilog or PSL assertions, which we can then use downstream. So here's a refinement. We have the gear and the door. We now introduce the handle. And the difference with this FSM is now we have the notion of an idle. So we're already ticking. So we're on the ground. The pilot wants to retract the landing gear. So we open. And now we're in the process of opening. We just have a notion of a cycle where you're idling until you complete the open, or you close because you want to change your mind. This is pretty complex. So you think about actually verifying this example. Already, the number of tests you have to run, because the pilot actually can just move the handle up and down like this. At any time, you can shortcut the actual operation. So already you have some notion of the test plan of how you're going to test this. In further refinements, what you need then to do is these idle loops, which at the moment is the notion of a cycle, they need counts on them. Because if you go to the Airbus specification, it'll tell you precisely how much time it requires to do that before it's completed. And so now what we do is we add the timing constraints, and what we can show is through refinement proof is that it still obeys the original properties of the system, that you can never have the gear moving when the door's opening or closing. At this stage also, we can start talking about we don't want any deadlocks. So as we're refining the system, we don't want to introduce deadlocks. So what we're able to do is we can use the model checker to try to show absence of deadlock, run it for a long time. But it's also possible with this system, and it's been done on this actual system, is actually to prove that illegal states of the gear, the door, and the handle are not reachable. And then also prove that when you're in a legal state, you can always get to another legal state. So we write invariants to do that, and we actually prove at this level. And then those proofs are preserved as we refine the system. We can still model check. We can generate tests. So we'll generate a set of tests. What we'll say is what we want to be able to do is test, first of all, the scenario where the pilot just moves the handle once. And we can develop a test from going to there and coming back again. We'll then develop a set of tests where the pilot's allowed to move it a couple of times. Once you get up to about 5 or 6 times, this really explodes. And we talked about state explosion this morning. If the pilot is moving this often, and he can, then the number of tests. But you need to be aware of that when you're verifying the system. We can generate tests for, I think I've been generated tests up to, say, 7 movements of the handle. When you start putting the timing in, that probably is feasible with the deadlines that you're dealing with. But already at the stage, you're thinking about the testability of the system. And we measure MCDC. We're measuring the coverage of the system when we run the tests, when we do the model checking, that all the guards of the events, so you've seen the events, all the guards can be independently set to false for all the states. So we have the notion that the actual model that we're using to develop the tests, the set of tests, actually achieve coverage of the model. And then what we can do, of course, is when we run those tests against the RTL implementation, we can do the structural coverage analysis. And this is effectively a step in the middle. So if you have a gap in your RTL coverage, you can go back to the specification because it's traceable from the implementation to the specification. But then you come to another step to the model. And you say, why haven't I got coverage? If I've got coverage here but not the implementation, there must be some problem with the specification. So you revisit here and then at the implementation level. OK, so the application areas, domains for this, where it's actually been used and used down to sign-off and certification, is aerospace, DO254, which is the hardware, digital hardware, 178C, which is software. The system's been used on signaling, Alstom Transport and Atkins Rail in the UK are using Rodin and have used Rodin on signaling. Automatic train doors, driverless trains in the Paris Metro. Energy distribution, I showed you an example for smart grids. And it's also been used on automotive for developing lane centering systems, cruise control, automatic gearbox control. And the other large area of use is defense, UAVs in particular, certification of UAVs. So just to summarize, so what Rodin supports is formal modeling, which is supported by strong formal verification tools, both model checking and proof, to establish deep understanding of the specification and design, with those links to the specification and the design. You can then use simulation-based verification to ensure that the formal models exhibit this expected behavior and timing in the target physical environment. And then we have model-based testing for systematic generation of high-coverage test suites.
Thank you very much. Thank you. Just so you're aware, I know not all the slides are printed in the hand up, but they will be on the website. Are there any questions?
Just wondering if you've extended this into fault tolerance, for example, if there's a failure in the liquid burner, transmitting up, down, up, down, up, down.
Yeah, so the question is, do we look at this in terms of fault tolerance? So we'd have to go back to the original safety constraints. So this is like the good behavior. If you go back to here, this is dealing with effectively what I've dealt with in the talk is how you identify these hazardous control actions. And now you have to determine how unsafe control actions could occur. And so yes, now you do the next stage is actually to go through each of these particular parts of this diagram to see where things can possibly go wrong. So we have the notion of the handle. So issues and extend, retract. What happens if there's a failure there? Then it doesn't get to here. Same as here. The controller issues an open door, a closed door. What happens if there's a failure of getting to the actuator? What happens if there's an actuator problem so that the message doesn't get here? So the second phase is you actually do a safety analysis on each of these and imagine the scenarios where there can be faults on that particular control variable.
Any more? There's one. Back. This is what you hit.
Hello. I wonder if you can approach from the right verification. If I would like to know that everything is safe and was any number of movements of the hand instead of just that.
Just 7. So if you wanted to do it for 20, it's not within the ability of the model checkers to be able to check the number of states. That is beyond that would be a state explosion. But remember, there's also a constraint because it actually there is a minimum amount of time that the pilot can actually take. So when you put the latency of the actual handle movement, some milliseconds, you compare that with the actual time it takes to perform the whole procedure, then 7 movements is, I think it's 6 actually for Airbus. There are 6 possible movements that can get there. Obviously in the abstract model, we would like to verify as much as possible. But in this case, what happens is when you constrain it with the timing, the state space reduces.
When you're beginning this process, and you sit down with the domain experts, and you're trying to develop language which defines the safety constraints, is there a methodology or a strategy or a grammar that you use? Because the domain experts will have their own concerns and ways of thinking, and you're trying to wrest those into the beginning of this.
Yeah. That's right.
This decomposition process. So how do you actually do that, sitting down with an expert and talking with them well?
The abstraction we use is the state machine, because that's common to us and to most of these controller designers. So we like to talk about state machine transitions, and the guards on those transitions and the actions. And then properties derived from that.
One question for you. Have you applied this to any of the sort of security aspects of this?
Yes, I think there's a very nice paper in ACM by the same author of Safer World, is that this mechanism can be applied, STPA can be applied to safety as well as security, and should be done at the same time.
Have you got any examples of security properties?
I don't have any.
Okay.
They tend to be secret.
Okay. Is there more questions? So I think we're moving there. Thank you, Jonathan.